All right, let's get the show on the road. Hello, everyone. Hope you're all well. Welcome to another edition of Math 1203. Uh, wow. So much has happened since I last saw you. So my brother had a baby on Valentine's Day, so everyone calls me Uncle Jhevon now. Um, this has been migraine week for me. Pretty much every day this week I've been having really bad headaches, including today, but it's not so bad today, actually. So I don't know what I told you because I told some of my other classes and I don't honestly I don't remember what I said to you guys the last time I saw you. So we're gonna have to review. Okay, but we have a lot to catch up on because we missed a class this week. So now the other calculus class I have is ahead of you guys, and now everything's out of whack. I don't know what I told you, what I told them. Let's not waste any more time. Let's actually just get into it. If anything is important, I will let you guys know at some other point. That's important. I didn't even remember I put that in the notes because I created these notes like last week. Okay, so let's actually get into it. This is yeah, I'm hopeless. All right. So announcements, because last week we had a couple students who tried to get into a quiz or something, and they emailed me in like a cold spell. I can't see the quiz. We didn't have a quiz last week. The quiz schedule is in the syllabus. We only have quizzes on the scheduled dates. There are no pop quizzes or anything like that. So last week we didn't have a quiz. So the dates of all the quizzes and the tests, they're already in the syllabus. I mentioned them in lecture 0. Make sure you know when the quizzes are, so you don't try to get into a quiz when there isn't one or anything like that and start freaking out. So we have about five. I want to say five quizzes throughout the semester. The dates are already set. Those are the days. So make sure you know that. Check the dates because I'm not always going to remind you about them either because, I have it kind of already set up to go. So there might be a week where even I don't remember, oh, they have a quiz tomorrow, and I won't say it. Okay, so it's up to you to pay attention to the due dates. With homework, it's a lot more lax, as I mentioned. Homework, there are 2 major due dates, one in the middle of the semester and one at the end of the semester. But for quizzes and tests, you need to know when the dates are. So I just wanted to make sure about that. And in terms of time commitment, quizzes on average, they should be about 30 minutes, but depending on the kind of things I'm teaching you guys, they might go a little longer, so no more than an hour. The tests are going to be like an hour and 15 to an hour and 30 minutes, so pretty much the entire class time. The final is going to be like 2 hours long or something like that, right? It's kind of going to be a combination of test 1 and test 2. Nothing is cumulative except the final, right? So not unless it's incidental, right? So I mean, it's math, so you're always kind of going to be doing a lot of the same things, but it's not because I'm testing you on the same topics all the time. Like you're going to need algebra skills throughout the course, but I'm not testing you on algebra. I'm testing you on as far as the calculus topics are concerned, the quizzes and tests, they are not cumulative. So they only test you on certain sections. The final is the only thing that's cumulative. Okay, what else do I want to remind you of? I think that's it for now. This is what being prepared gets you, because apparently this is the last thing I spoke to you about, and I prepared this literally right after the class. So I guess this is where we stopped. So I kind of think I know where we are now. Yeah, last time we introduced the idea of limits, and maybe I should actually go back to make sure that we remember all of that stuff. Yeah, last time we spoke about average rate of change. Nothing new there. As a concept is very important, but we'll get back to that later on. But the formula is basically the difference quotient. You should know how to compute that. The A and B version is more useful for this particular application. And usually I'm going to ask you, here's a function, here's an interval, find the average rate of change. It's not going to get any more complicated than a question of that type, right? So for this question like that, it's going to be part A of some question that I'm going to ask, hey, by the way, here's a function, find the average rate of change. And then part B, I'll ask you to do something actually interesting. Okay, so this is just something to know. We did an example of that. I didn't think we need any more. We're actually going to work a lot more with difference quotients in the future, believe it or not. Told you about the interpretation, though, why it's interpreted as average rate of change. We spoke about what is calculus, very heady stuff. Then we went on into the idea of limits. So limits is a very kind of weird thing for the uninitiated, because it kind of goes against a lot of the things that you learned about in math before. Limits are all about approach, getting close to something. It's not about being at the point. It's not about plugging in a value and computing it, like at least not by concept. It's not about the things that you're used to things being about. It's kind of about, if this gets close to this, does that get close to that? Right? That's kind of what a limit, and close at this point seems very arbitrary because we're not doing the real mathematical definition, but it just means you should be able to get as close as you want. You should be able to get inch closer and closer and closer if you want to. That's sort of what we mean there. So what I do want you to get in your brains is that the limits, you're really tracking the y values, the behavior of the function, right? So the limit is what the y value gets close to as the x value gets close to something, and that is the notation. As x gets close to a of my function f of x, what does my y value get close to? And you need to be able to state this thing uniquely, unambiguously. Okay, so we did a couple of examples like that. This one, we noticed, hey, we would kind of get the same answer if we did just plug in. So what is Jhevon telling us about not being able to plug in? Because there are times when you won't be able to plug in, like in this example, right? We could simplify that, and then you'd realize, oh, this is kind of an answer I would have gotten if I plugged into this simplified version. But even that, you won't always be able to do. Then we did another example, this kind of example, because I really wanted to get into your heads that limits aren't about being at the point, they're about getting close. So what was the limit as we approach to here? The filled in point is, it's just there to trick you. It doesn't matter if which of the points or if any of the points are filled in. Limits don't care, irrelevant. We don't care about being there. We care about what happens as we get close to there. We notice here, as we got close from the right, it seems like the y values were approaching 7. As we got close from the left, it seems like the y values were approaching 0. And hopefully now we've caught up to speed. So that's what brought us to a civil war. Is the answer 7 or is the answer 0? Both sides have very valid arguments, as both sides had very valid arguments, but they were kind of ended up both wrong, because this kind of means there is no answer, because there needs to be a unique, unambiguous answer. The y value needs to get close to one thing as the x gets close to 2, and that did not happen. So here we say that the limit does not exist, right? So we don't use the word undefined for limits, we use does not exist. Okay, so I think we're all caught up now. So now let's continue. One thing you might notice here is that, well, I mean, if limits are about talking about the y values of functions and talking about the behaviors of functions as we manipulate the input in some way, it kind of feels like we've been cheated with this answer. I mean, does not exist. Yeah, I mean, technically by the definition, we don't have an answer, but I can clearly see what's going on with a function. I can describe its behavior exactly. I know that if I'm coming from the left, it's going to 0, and if I'm coming from the right, it's going to 7. There should be a way for me to express this idea without just telling everyone, I don't know, it doesn't exist, right? And there is. So this last example I gave you guys to introduce you to a new notion called one-sided limits. I should make a notion of one-sided limits. New subtopic. Okay. One-sided limits. So the idea is pretty much the same as a limit, but we're allowed to only care about coming from one side at a time. That's the idea. So in Calc 1, There are two. In Calc 3, this idea actually doesn't really exist. Does not exist. Okay, never mind. So in Calc 1, there are two one-sided limits, and here is the notation. So let's see what color I used before. I used pink coming from the right. I don't know. That's kind of psychologically, never mind. Okay, so when you want to talk about something coming from the right, what you do is you put a little plus sign as a superscript on this number, okay? So that's like a plus a little bit. So a, remember, is the x value, but you're at that value plus a little bit, which means you're on the right side of that value. This is a limit that we use to measure things coming from the right side. So we can write this notation to mean the limit as x approaches a from the right. Okay, so it's basically a one-sided limit. You kind of ignore the left side and look at only what's happening on the right side. And to indicate that you're doing that, on your limit symbol, you write a plus sign in the superscript, like in the power to the top right of that number. So remember, this does not affect the sign of anything. It's just an indication that talks about what direction I'm heading into. So it doesn't change anything else to positives or negatives or anything like that. Okay. Similarly, we have another notation for coming from the left, and I used green for the left. We've just put a negative sign. So you're a with a little bit negative, a little bit less than a. You're less than a, but you're approaching a from the left side. And I don't know which way the camera is going to show, if it flip mirrors my image or whatever. But this is from the left side. Okay. And so that deals with one-sided limits. So for example, in the previous example, we could say that the limit as x approaches 2 from the right of our function, and the limit as x approaches 2 from the left of our function. And it turns out we can get answers to each of these individually. So if we go back to our picture here, you will notice here that as I get close to 2 from the right, my y values are getting close to 7. So I can say the answer here is 7. And then if I go back to that picture and I look, okay, as I'm coming from the left, 2 is left, 2 with a little bit negative on it. So it's like 1.99, 1.999, 1.999, just getting very close to 2 from the left. Notice that I'm on this part of the function, the y values are decreasing, going down to 0.
Professor?
Yes.
Does this only happen with piecewise functions? Or are there other cases of it?
If what? No, this is across the board. What I'm telling you, this is a general concept. It applies to anything.
Okay.
I'm using a piecewise function to illustrate the idea, but this is always an idea that you will be using. It also applies to non-piecewise functions. So, for example, I'm actually going to cover more examples. Yes. Okay. So they're over here. Huh. I saved those from last time. Okay, we'll discuss these. I don't think that was for you, but copied down what I did with the other class. And so let's actually do more examples. So you'll see what I'm talking about. So this idea that I just mentioned is actually going to come into play with examples like this, and it's not a piecewise function. There is something else I want to mention though, again, more of a definition type thing before we get into more examples. This also leads to the notion of the existence of limits. So clearly, last time we introduced the concept of a limit not existing. So you might wonder, in general, when does a limit exist? Well, so here is one criteria. The limit only exists if both the limit as x approaches a from the right of f of x and the limit as x approaches a from the left of f of x exist and they are equal. The they refers to the one-sided limits. So that's another criteria. So this is something that it doesn't matter if the function is piecewise or not. This should be something that you should be noticing. Is it the same as I come from the left and the right? This was something that happened automatically in our previous examples. You'll notice here, as I came from the right, we went down to 5. As I came from the left, we went up to 5. The left and right hand agreed. Here, as I came from the right, we went down to 4. As I came from the left, we went up to 4. The left and the right hand agreed. Here, come from the right, we get 7, left we get 0. They do not agree, does not exist, right? This is an equivalent criteria. To make sure that a limit exists, you can also judge it from both sides at a time, which it might be necessary in some cases. We'll see examples where they're necessary. But definitely a piecewise function is one of the situations where this is going to happen. You know that, well, if it's a different thing when x is greater than 2 than less than 2, then yeah, you have to look at each side individually. You can determine the one-sided limits, and then the overall limit is just determined if both of those exist and they give you the same value. So a piecewise function is obviously one situation in which you're going to have to make such a consideration. It's not the only situation, though. This is a general thing. The one-sided limits must exist and agree for the overall limit to exist. I also want to point out it's possible. Note, it is possible for even one-sided limits not to exist. We can have various combinations of existence, non-existence. But one thing that is always true, this guy does not exist unless this guy and this guy exist and agree. But other than that, don't think that a certain pattern has to happen. You can have various patterns. So for example, I can do something like the following. So I could have a function where it's like, boom, and like that is A, and then there's a gap here and like that, right? So I could have that. In this case, the limit say this is 1. In this case, the limit as x approaches a from the left of f of x is 1. The limit as x approaches a from the right of f of x. Oh, maybe that would be a good thing to actually ask you guys about to see if you understand limits. What is the limit as we approach from the right? So we're going to do that same idea. As I get super close to a from the right side, what part of my function am I on?
One.
What part of what? Come again? What the question was, what part of the function am I on? Right. So remember we did this idea. So it's like when I'm getting close to 2, what I do is I translate that to my function to figure out where on my function I'm at. And then I transfer that over to the y value to see where the y value is at, right? So I'm asking the same question now. As I'm getting close to a from this side, and I try to transfer that up to my function, what part of the function am I on?
You're not on the function?
I'm not on the function. What does that mean? So this means we can't get close, right? So I know close is an arbitrary thing to us at this point, but close should mean as close as you want. I should be able to get as close to a from the right side, as close as I want. But obviously that's not the case. If I'm coming from the right, the closest I can get to a is right here, right? So this is the closest we can get to a from the right. Right? Which is not as close as someone might want. Someone might want to get closer, and that should be provided for. Turns out that this does not exist in this case because we can't get arbitrary close. We can't fulfill the definition. So I want to again, limits are a very nuanced idea. I want to make sure you get the nuance. When I say the x value gets close to something, I really mean you should be able to get close to something. Like if there's a gap between you and that something, all bets are off. You can't get close. You should be able to get as close as you want, right? How close? Within 1 unit? Yes. Within half a unit? Yeah. You should be able to like as close as anyone wants. They should be able to get closer, right? If you can get to within any distance of that value, someone else should say, I want to get within half the distance that you got, and it should be possible, right? That's what close means. It means really close, right? I cannot get close from the right. So it turns out that the one-sided limit here does not exist. Now, the moment that the left-sided limit exists and the right-sided does not, that automatically means does not. And you know that because left and right don't agree. Right? Or you could have an example like this one for the same kind of thing. So here is my point isolated right there. There's a gap between it. That's my point A. Then again, my limit as x approaches a from the right does not exist. My limit as x approaches a from the left does not exist. My limit as x approaches a, well, it's weird. They technically agree in this scenario, but it would also be does not exist because they don't exist. So the overall limit does not exist, right? I can't get close. So you can have all sorts of combination. One or both of your one-sided limits may or may not exist. And and then you use their values to determine if your overall limit actually exists, right? So you can have all sorts of combinations, but the fact of the matter is, if these two guys don't make sense and agree with each other, then this guy is not going to exist. That's always true. But other than that, you can have various combinations between them, right? So you don't have to have anyone existing. The limit doesn't have to exist because you want it to exist. It's just not a thing. Okay, so existence of limits, that's something we want to make sure we understand. So let's actually do more examples just to get used to this. Okay, so let's look at this one. Limit as x approaches 0 of 1 over x. And we're going to get into some shorter ways to do things today, but we're still kind of being very concepty and nuancy. So I want you to see what's happening on the picture, because knowing what that happens with the picture can actually save you in a bunch of situations. But no, for finding limits, you're not always going to have to be drawing pictures and stuff like that. I just want you guys to see and understand what's really going on behind the scenes. Okay. So 1 over x, you should know what the graph of this looks like. It was on one of the quiz ones and stuff. So looks like that. And looks like that. Should be symmetric, not drawn to scale, obviously. Okay, so now let's test the new concept. What is the limit as x approaches 0 from the right? This is where you guys chime in. Madeline?
Wouldn't it be that it does not exist?
Why would you say that?
Because from the right, because on the right side, which would be the second one, it doesn't go into 0 and it's just going along.
So the 0 is right here. So what do you mean it doesn't go into 0?
Like it doesn't go even near it. Like it.
Well, I mean, for 1 over x, it's asymptotic, right? So it gets closer and closer and closer and closer over time. It never touches, you're right. But it's asymptotic. It gets closer and closer to 0. Yeah.
Wouldn't it be infinity?
It would be infinity, right? So remember, for limits, we don't care whether we can get to 0. The fact that this graph doesn't actually touch the y-axis, completely irrelevant, not relevant at all when it comes to a limit. The fact that I can get as close to 0 as I want, because this curve, the higher up it goes, the closer it gets to 0, that's good enough. Anyone can get closer to 0 than they currently are coming from the right side of this function. So yeah, for this concept though, you'll notice that you're not able to actually pick a value, because if someone says, oh, the limit is 1,000, you're like, well, I can get, and that happens here. Someone can say, well, I can get closer to 0 and I get higher than 1,000, right? So it's like whatever number you pick, someone can move closer to 0 and get a higher number. So it turns out the closer we get to 0, the bigger the y value gets. And then I get closer to 0 and the bigger it gets. And then closer to 0, bigger it gets. There is no single y value that I can say that if I get close to 0, that's what I'm approaching. The closer I get to 0, the bigger the y value becomes. That idea is expressed with infinity. Okay? The y values just keep getting bigger and bigger the closer I get to 0. Now, what if I am coming from the left?
Would it be negative infinity?
Negative infinity. the closer I get to 0 from the left side, the smaller and smaller and smaller the y values become. They become more and more negative. Whatever negative number someone tells me, I can get closer to 0 and get a lower negative number, right? So, because it keeps going down forever and it keeps getting closer to 0 as it does this, right? So there is no y value. So, all right, moment of truth. What does that mean for the limit? Okay.
It wouldn't exist.
Does not exist because they don't agree. Yeah. Okay. So now I'm slowly introducing you to the concept of throwing infinity into the mix, which, you know, nothing on my sleeves. I did mention that limits involving infinity. So infinity is for us a legitimate answer that we can get. It does talk about the behavior of a function. Infinity just has the idea of us describing that something is happening without bound. It just keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. So it just keeps going to the right of the number line or to the left of the number line, and we can't stop it or bound it. So that idea is what's captured here. So hopefully that is clear. Something funny is going on here. Mm-hmm. Okay. All right. So let's go to another example. This one is the next one. I should start cutting these so I don't forget which one we actually did. X approaches 0 if 1 over x squared. So going to take the same approach because I want you to see what's happening. We know what the graph of this guy looks like. Tell me about the limit as I approach 0 from the right of 1 over x squared. Tell me about the limit as I approach 0 from the left of 1 over x squared. And then finally conclude, what is the limit as x approaches 0 of 1 over x squared?
Both would be
Right side.
Oh, positive infinity.
Yep.
So that means that the limit would exist.
The limit would exist and it would be?
Infinity.
Well, positive infinity. Everyone agrees. Yay. Right? They don't become a number, but they all agree that the number just keeps getting bigger and bigger. And so that would be an answer. Now, I want to bring something to your attention here. So examples like this is why a lot of students walk away with the notion that, oh, division by 0 gives us infinity because I have 1 over x squared, x is going to zeros, which means I go to 1 over 0, which gives me infinity, but that is incorrect. You will notice in the previous example, we didn't even have an answer. It was meaningless. Division by 0 doesn't actually happen. So that's what I want to point out here. Note, we do not, it's not one word. We do not actually divide by 0. Remember, limits don't care about getting there, right? The limit is not saying the x is 0. Limit is saying x is getting close to 0. We're getting close to dividing by 0. But denominator, as you will notice, its squared is always slightly positive. Right? So the x never actually gets to 0. It gets very close to 0, but because the x is squared, it's always slightly positive. So I'm going to introduce a little bit of notation here, which admittedly is somewhat informal, but it is something that I would allow a lot of people use it. So we can express this by saying that, the limit as x approaches 0 of 1 over x squared is 1 over 0 plus, right? So it's like 1 over 0 with a little positive charge, not quite 0. And yeah, that's infinity. Positive infinity, specifically. Just saying 1 over 0 is still meaningless. You cannot divide by 0. I do not want you to think that's a thing. We're not dividing by 0 because we're using limits. We're getting close. So we're 0 with a little positive charge. It's not really 0. It's 0.0000001 or 0.1000 zeros and then a 1 or something like that, right? It's slightly positive. It's never actually at 0. We're just getting close to it. So here the denominator is approaching 0. It never actually gets to 0. Also, I wanted to note, maybe I should start. Also note, even approaching division by 0 can have weird behavior. So again, it's not always infinite. Sometimes it's also just meaningless, plain old and simple. Sometimes it is also DNE, as in the 1 over x example. And possibly some other real number. You could get a finite answer. So the idea is, even when we're getting close to 0, do not believe that there's some standard answer. It will vary depending on your situation. So here, the same thing happened. We got close to dividing by 0, but in this case, we had no answer. Here, when we got close to dividing by 0, we had an answer, but it was infinity. There are going to be other times when the answer could be 7 or 9 or 17 or 1 over pi. You'd never know. Division by 0 is such a crazy thing that even when we get close to doing it, all sorts of crazy things can happen. So you have to really pay attention to the situation that you are in currently. Okay, so I just want to make sure that I'm pointing that out. Maybe some more FYI on use of notation. For the limit as x approaches 0 from the right of 1 over x, I could have described that as 1 over 0 plus. That goes to infinity. And the limit as x approaches 0 from the left of 1 over x, I could have described that as 1 over 0 negative, which is negative infinity. And that's because I saw the right side was going up, the left side was going down. It's not that, and it's not that this is 0 plus because that was 0 plus, right? And so the limit, the overall limit, does not exist. Notice if I had another example. Let's make it a little more interesting. If I had something like limit as x approaches 1 from the right of 1 over 1 minus x, limit as x approaches 1 from the left of 1 over 1 minus x, then in this case, how you can think of this as, okay, x is getting close to 1, which means my denominator is getting close to 0. But let's see. X is getting close to 1 from the right, which means it's slightly bigger than 1. So don't think of it as 1. Think of it as 1.01. So if I have 1 and I subtract a number that's slightly bigger than 1, I get a slightly negative number. So I get the denominator is approaching 0, but slight negative charge, right? That's the thought process you're going to go through. Then you're going to be like, oh, that's going to give me negative infinity, right? So you can think of it that way. So here you can kind of reason through an answer, but it's not like I automatically think it's positive infinity because it's 1 with a little plus sign. Remember, this plus sign has nothing to do with the sign of the answer. It's a notational thing that indicates direction. Similarly, here, with that same reasoning, okay, I'm approaching 1 from the left, which means I'm slightly smaller than 1. So I'm like 0.999. So if I take 1 minus 0.999, that gives me something slightly positive. It's getting closer to 0, but it's slightly positive, and therefore that is positive infinity, right? So then if someone says, oh, what is the limit as x approaches 1 of this function, I would say it does not exist because the right hand and left hand don't agree, okay? So again, the concept might still be a little fuzzy to you, but with a lot of practice and going through your homework and going through and doing studying, hopefully it becomes clearer. But I just wanted to point out some things that might be pitfalls to you in the future, based on my experience of teaching calculus every semester for the past 10 years. Like literally every semester I teach calculus. Can you believe that? Why is calculus so popular? Well, I mean, it's very useful, don't get me wrong. Okay, so yeah, just some things getting you, the goal is to get you a little more used to the nuance, and again, to make you very cautious of even approaching division by 0. Division by 0 doesn't exist, but even when you get close to doing it, all sorts of things can happen. You have to be really careful how you navigate the situation. Let's do this. Cut. Okay, so we're getting a lot of mileage out of these examples, but I really wanted to, there are a lot of levels, like ogres and onions. There are a lot of layers to just looking into one of these problems, and you can have a really, don't laugh. Okay, it wasn't that funny. Okay, so Sarah's like dying over here. Ogres have layers. You shouldn't encourage me because now I'm going to go off on a tangent. Okay, so let's get to some more layers with these problems. So here's, again, our old friend 1 over x squared. Same guy we saw before, but now I'm asking something very interesting, something very, might seem crazy or crazy genius, no one knows, right? I'm actually letting my x itself go off to infinity, which is, huh, what? Okay, I'll put that, maybe I'll highlight that in a different color. So here I'm asking the question, my x isn't even getting close to a number. Just let x go off to infinity. X is approaching infinity, like far to the right. Are we there yet? No, keep going, right? We're at a gajillion, bajillion, gajillion. Are we there yet? No, keep going. X just keeps going to the right as far as you can without bound, right? And I can ask the question now, what is the limit, right? So what do you think?
Is it 0?
It's 0, right? Now, it never actually hits 0, but it's a limit. We don't care that we never actually hit 0. It gets closer and closer to 0, right? As I'm moving far, far to the right, as I keep going like that, I'm on my function like this. If I track that over to the y values, I keep going like this. Now, the thing never passes 0 because the graph itself never goes under here. It also never hits 0. It stays above 0, but it keeps getting closer and closer to 0, which is what the limit cares about, right? So it's actually 0 is the answer. Yeah, so yay for concepts, right? It's not even an actual calculation or thing that I can plug in. but it's just the concept of what's happening. I'm getting close to this. What does it mean to get close to infinity? It means just keep going to the right as far as you can, right? And then what's happening to the y values? Here's another one. Our old friend e to the x, esteemed by many esteemed mathematicians as the most important function in all of mathematics. For sure, it's the most important function in all of calculus. We should know what its graph is. It passes through, what does it pass through here on the y-axis?
Two-point something.
No.
Oh.
Another guess? This reminds me of a meme. There's a meme out there where it's like more advanced math, right? So you're going like from algebra, pre-calculus, calculus 1, calc 2, calc 3, you're right, you're going off to the more advanced math. And then over here is like ability to do simple math. And then the graph is like this. Which is, it's kind of true. Yeah, ask me to multiply two-digit numbers in my head. I know how to do it on paper. I can't do it in my head anymore. Back when I was a little kid and we were just learning about arithmetic on our times tables, I could do it. But it's like now math is much more about concepts than numbers. It's like I don't play around with it. So you forget things. So it's like with here, if we weren't in calculus and I didn't tell you what E was about and why it's important, you would probably get this answer right away. On the y-axis, our x value is 0, right? What is the y-intercept is the question that I'm asking you. What would you do? You plug in 0 for x. E to the 0 is anything to the 0.
1.
It's 1, right? So yeah, you're like, oh my God, he's asking me what is the y-inter. He asked me what it touches the y-axis. This is some advanced calculus concept. No, it's plug in x equals 0. It's always going to be that, no matter how advanced in math you get. Y-intercept happens when x equals 0, whenever you're in 2 dimensions. Okay, so you would get 2.718 blah, blah, when x equals 1, right? So this goes up to e, which is roughly, you know, the 2.718, blah, blah, blah. Right? Because you plug in e to the 1, which is e. We had that as a law of exponents. So that's where you would get it. Okay, so it passes through 1. Okay, that's beside the point. I just wanted to check because my other class actually messed up on this too. But I just remembered this meme, and it's because, you know, Sarah encouraged me with. Okay, so now, what is this answer? What would you say? As my x goes off far, far to the right, I'm on my graph and we're doing this. Maybe I shouldn't. As my x keeps going off like so, I'm on my graph going off like so. What are the y values doing?
Would it be infinity?
Would be infinity. I should really be boxing the answers that we're getting here so you're not confused as to which one of these limit things to look at. That's D&E with an exclamation mark. Very excited. Okay, so yeah, infinity, right? As my x gets large, my y gets large, and they both get large without bound, right? That's basically what I'm trying to say. That's what this statement means, essentially. If I'm on the function y equals e to the x, as my x get large without bound, my y value is going to get large without bound. So this introduces the notion of limits involving infinity. There are two kinds we care about. And a mix. We call a limit as x approaches a of f of x equals L an infinite limit if our L is infinite. So if the y value is infinite, if the output is infinite, we say it's an infinite limit. We call the limit as x approaches a of f of x equals L a limit at infinity if the a is plus or minus. So we can take the limit at infinity, which means our x is going to infinity, and the y value can do something else, or we can say we have an infinite limit when the output is infinite. So examples, we've actually looked at the examples already. So an example of the first one, the limit as x approaches 0 of 1 over x squared, it's equal to infinity. We saw that. That's an infinite limit. The limit as x approaches infinity of e to the x, that's equal to infinity. That's an infinite limit. Example of this, we saw the limit as x approaches infinity of 1 over x squared is 0. We also saw the limit as x approaches infinity of e to the x is infinity. So these are both examples of limits at infinity because they go to infinity and beyond. Okay, so here the answer, when the answer is infinity, we say it's an infinite limit. When the input is approaching infinity, we say it's a limit at infinity. Of course, note, we can mix. You can have both. So not to be a tongue twister here, but example, the limit as x approaches infinity of e to the x equals infinity is an infinite limit at infinity. Right, but where the infinity shows up, infinite limit or limit at infinity, if the infinity word shows up before the limit versus after the limit, we're talking about different things. Okay, but you can have both. What else do I want to say? All right, now I think the next thing I want to talk about is the properties and strategies behind limits. So the examples that we've done so far is really to introduce you to the concept of a limit and make sure you understand it as an idea, what you should pay attention to, what you should not pay attention to, really hammer it home that limits are about getting close to something and not actually being there. Limits are about really seeing what the y value is doing when the x value is getting close to something, introducing the notion of infinity into the mix, and really kind of conceptually getting this down. However, not all the time, ain't nobody got time for that all the time, right? Sometimes you want to be able to, oh, here's a limit. I need to compute the answer quickly. I need a mathematical, algebraic way to just do it. I can do the calculations. I don't need to worry about the graphs or who's getting close to what, right? So that's what we're going to get into now. For that purpose, I'm going to say about the algebraic properties of limits, which are very nice, as we will see. And then I'll tell you about some strategies, right? So if I give you a random limit problem, how do you approach it? How do you know what concept to apply at what point, right? So that you can get through the test, feel very confident, know you're doing it right, getting a good grade, all that good stuff. So now let's talk about the properties. And when I talk about properties, and usually in math class, when we say properties, we mean algebraic properties or computational properties. Properties of limits. Turns out limits are one of the nicest things. I mean, the concept is very weird at the moment because it's different from the kind of things that you've seen before. It's the main thing that makes calculus calculus, right? This is why calculus is different from the other math that you've done before. It's because of the concept of a limit. That's where we get the power of calculus. So it seems weird, but actually, computationally speaking, it's very nice. It's literally nicer than anything you've seen before. And what do I mean by that? Let me show you. Assume the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x, some other function, equals m, are limits that exist and are finite. That's actually very important because like division by zero, infinity is also where something happens, weird things can happen when you throw infinity into the mix. So I'm saying they're not infinite limits. LM regular, don't use regular, real numbers. It's a very pompous thing for them to call them. We're the real numbers. Are you a real number? Okay. So, and let C be a constant, just any real number. Now, here are some things that are going to make calculations nicer for you. So, 1, the limit of a constant is, drum roll, the constant, right? What is the limit as x approaches 7 of 18? 18. What is the limit as x approaches infinity of 5.2? It's 5.2, right? The limit talks about what the y value is doing. If your y value is a constant, that's always what it's doing. This is what it does, right? So limit of a constant is just the constant, right? So that's cool. So you don't have to like draw a picture and like track stuff. And no, if I see the function as a constant, that's the answer. Here's another thing that's cool. Let's say I have the limit of a constant times a function. It turns out that I can factor that constant outside the limit. Constants can factor outside of limits. So if I know what the limit of that function is, which in this case, we're assuming it's L, I know what the limit of any constant times that function is. I'll just take a constant times the answer, right? So if we look at this, one of our previous examples, I don't know. Like this one. If I were to multiply this by any constant, like what if I put a 7 here? The answer is still 0 because the answer will become 7 times 0, right? So me knowing what happens to 1 over x squared, I automatically know what happens to a constant times 1 over x squared, right? So that's a shortcut, right? So that's very nice. Constants can factor outside of limits. Here's something else that limits can do. Limits distribute across sums. So if I have two functions, I'm adding or subtracting them, then the limit of the sum is the sum of the limits. Limits distribute across sums. Very nice. So that would be L plus or minus n. Now, here's something crazy, which if you have any experience with math, you're going to realize how crazy it is that I'm saying this. Might not be crazy to you, but it is totally crazy. Limits distribute across products. What? The limit of a product is the product of the limits. Now, why is this strange. You're like, well, so what? Power is distributed across products. This distribute across products. You know, you can probably point to a lot of things that distribute across products. Okay, I dare you. Point to something that distributes across both sums and products. I'll wait. What else do you know is that nice, right? The things that you're used to distributing across sums don't distribute across products, right? Like you have a constant, if you have a constant multiplier and apply the distributive law, it'll distribute across a sum. It does not distribute across a product, right? If you have 2 times x plus y, the answer is 2x plus 2y. If you have 2 times x times y, it's not 2x 2y, it's just 2xy. It doesn't distribute across a product. A power distributed across a product, right? Xy to the a is x to the a, y to the a. However, powers do not distribute across sums. X plus y to the a is not x to the a plus y to the a, right? It's very rare for something to do both, right? Limits do both. And this is what I mean, they're very nice. Almost anything you feel like you should be able to do with a limit, you actually can, which is crazy, right? It can distribute across sums, it can distribute across products, it can distribute across divisions, which is somewhat obvious if you know it can distribute across products. But yeah, if I have one function divided by another function, the limit of the division is the division of the limits. I can distribute this guy. The only thing I have to look out for is the thing that Jhevon keeps warning us about, is making sure that m is not 0, right? As long as my limit of g is not 0, this is going to be the answer. So if I know how a limit behaves with the individual functions, I can immediately know how it behaves with various combinations of these functions. Limits, you can move them inside and outside of powers. Come on, does it ever stop? Okay, so if I have a function raised to a power, which means it includes radicals, for example. So if I have the limit of the square root of a function, I can actually move the limit inside the square root and worry about, and just ignore the square root, figure out what's going on the inside, and then apply the square root afterwards, right? So I can apply the limit inside first, and then worry about the power. Now, for us, we're going to make our power positive here because I don't want to worry about complex numbers, you know, or division by 0 or things of that sort. But yeah, I can move the limit inside powers. But who does that, right? Who does all of these things? Nobody. The limit does it. Even the things that we are going to develop using the limit, like the derivative and the integral, doesn't have all these nice properties, but limits do. So yeah, limits, they're awesome. You can factor constants in and out. They distribute across sums, they distribute across products, they distribute across divisions. You can move them inside and outside of powers. They go inside and outside of radicals. Like anything you would think you can do, which is crazy. As long as you obey the rules of the limits, you can do all of this, which is, so limits have very, very nice properties. So that's cool. Now, let's talk about strategies. Okay, so some random limits show up on a test. Strategies for computing limits. Okay, let's talk about strategy. Okay, so there are some examples that I have left for you. We're not going to do them today, obviously, because we're not going to have time. But like, look at all these guys. I'm going to leave these guys for you guys to try. Right, look at all this. Look at this. Look at that. Look how crazy that is. Okay, I'm going to tell you how to handle guys like this with these strategies, right? And you're not going to have to draw the graphs, like, because would you want to draw the graph of this guy? Like, no, right? Do you even know how to draw the graph of that guy yet? Not yet. We will learn actually in this class. So let's actually talk about strategies for computing limits. I give you a random limit on a test. Tell me what the limit is. How do you go about doing it? How do we compute? So I'll give you the strategies, then I'll let you guys go. I will leave the examples in the notes. I want you guys to try them on your own for next time. You can even try them in your groups that I set you up with. And on Monday, you can let me know what do you think the answers are. how do we compute some random limit? Right? So random limit shows up on a test or a quiz. What do? Panic? No, we don't panic. We follow these strategies. Step one. Maybe I should tell you a fact before step one. Fact. If f of x is continuous at a, this is something that we're going to describe later in detail, but it's going to be very intuitive for now. We'll describe in detail later. In this same section, I believe. It's also in your textbook. It's in the section where limits are. If f is continuous at a, intuitively means there's no break, there's no gap, there's no hole, there's no disruption. Everything flows smoothly. Then the limit as x approaches a of f of x is f of a. You can literally plug in the number. We saw this with the 3x minus 1 example in the last class before this one, right? So we saw x approaches 2 of 3x minus 1. We did that whole graph thing, but then we kind of realized, hey, I could have just plugged in x equals 2, right? 3 times 2 minus 1, right? So there are times when you can plug it in, but you need something called continuity for this to happen. Now, we don't know what that means in detail, but it basically means the graph just goes and there's no break. And if you know how to graph y equals 3x minus 1, you'll know that it has this property. I could just plug in the number whenever it's continuous. This leads to step one. Try to plug in. If this is doable, that's the answer. Usually. Right. Now, there are some weird cases here, like if it's a piecewise function, then maybe you plug it in and it works, but the other side doesn't agree. So you need continuity for this to happen, right? And you'll know that this can happen with continuity, right? So you try to plug it in. We saw an example of this. Example. So if I told you what is the limit as x approaches 2 of 3x minus 1, you don't need to draw the graph. You're just like, well, it's continuous at 2, just plug it in. The answer is 5. Right? Like, and that's a fully worked out answer. Right? You don't need to draw the graph and explain, well, but get close to the, no, this is what it is. It's continuous. I can just plug it in. So that's the first thing. You see a limit. I call it step one. I'm numbering the steps because I want you to think of it in this order. I'm telling you how to think about these problems. The first thing you try to look for, can I plug in the number? Chances are if you can plug in and it's not a piecewise function or anything crazy is going on, whatever answer you get when you plug in is the limit. Step two, we have seen that you're not always going to be able to plug in. What do we do in that case? Well, try to simplify so you can plug in. That's your next thing. The first thing you look for, can I plug it in? Second thing, if you can't, can I simplify so I can plug in? We also saw this example, limit as x approaches 2 of x squared minus 4 over x minus 2. Notice, can't plug in because I have division by 0. Do that, and Jhevon kills me. Can't plug in, right? So what do? Well, can I simplify this? And then at this point, your algebra brain kicks in. Oh, that's a difference of squares in the top. Can cancel this. This simplifies into that. And now I ask myself, can I plug in 2 now? Yeah, I can plug in 2. 4 is the answer. Let me actually write it out when you're plugging in the 2. That's a fully worked out answer. I want you to note, keep writing the limit sign until we take the limit. So notice that while I'm simplifying, I keep writing the limit sign there because I didn't actually evaluate the limit yet. I'm just rewriting to get to a point where I can do that. And then once we take the limit, take the limit is what we call it when we remove the limit symbol and we actually get an answer or evaluate to get an answer. Remove the limit symbol. So notice that here, when I plug in, there's no limit symbol left on the answer. Another thing not to do that I see students doing. But if you paid attention to my previous advice, you probably won't do this. Limit x approaches a equals f of x or something like that. What are you doing? What are you doing here, right? The equal comes after, right? Make sure you don't put the equal in the wrong spot. You can say the limit of f of x equals blah, or you can say the limit of f of x equals limit of f of x, right? The limit has to have the function right beside it. You can't separate. Limit by itself is meaningless. It doesn't mean anything to write by itself. That's like you writing sine. Sine of what? Sine of x, right? Sine of what angle, right? You can't just write sine by itself. It's meaningless. Same way you can't just have the limit notation by itself. You have to use it in a certain way, right? So I will deduct points if you misuse the notation of limits. So just so you know, being very clear here. Not a lot, but at least like 1 point, right? I won't deduct as many points as I would if you got the answer completely wrong. But if I notice that you're misusing the notation, I am going to deduct a point. So make sure that if you can't evaluate the limit right away, you keep writing the limit symbol until you get to a point where you can. Then once you know you can do something, you can now remove the limit because 4 is now the answer. You're not taking the limit anymore. You have taken the limit already. That's the answer. You don't need the limit anymore. Okay, but that's the second step in the strategy. Step 1, try to plug in. Step 2, can't plug in, try to simplify so you can plug in. Step 3, apply an appropriate special technique. We haven't done any of these yet. I just introduced limits to you. We haven't done any yet, but we will. And when I do the special technique, I'll tell you what situation you're allowed to use it in. So if the first 2 steps don't work, what you're going to do is you're going to look, does this problem have a pattern that coincides with a special technique I know that I can apply? And I'll give you guys a couple. Step 4. Try using graphs or table of values. Okay, so this is where graphing might come in. Sometimes none of these work, right? So if you look at example, the one we did earlier, limit as x approaches 0 of 1 over x, right? By the time you get to a test or quiz, you should know that answer by heart doesn't exist. But let's say this is a problem that we're approaching. Notice, can't plug in, can't simplify to plug in, right? How are you going to cancel that x in the bottom? So you can't plug in, can't simplify to plug in, no special technique here. At least not one that we know right now. So what do? Panic. You start to worry, oh, I'm going to fail this test. My parents are going to disown me. I'm not going to get into med school. No, that's not what you do. You go to the graph, right? So you have two options at that point. You can either graph, if easy. Definitely recommended here because the graph of 1 over x you should know. Or you can do a table of values, which you would do this if it's harder to graph, but you wouldn't really do it otherwise because it's very computationally intensive. So graph is like what we did earlier. You would actually literally quickly sketch a graph, see what's going on so you can visually see when you're approaching from either side what's going on. And then you'll see, oh, limit as x approaches 0 from the right of 1 over x gives me positive infinity. Limit as x approaches 0 from the left of f of x gives me negative infinity. And so here I can conclude the limit does not exist, right? Right? And I couldn't plug in to get that answer. I couldn't simplify to get that. I couldn't do anything. I couldn't computationally, I couldn't do anything. But conceptually, just by looking at the graph and using the concept of a limit, I could do it. So it's still important for you to know what I was saying above, all the stuff that we've covered so far, because there are cases in which you might have to pull out all the stops and go back to basics. Table of values is a very similar thing. The idea is, here's your x, here's your y, 1 over x. Remember, you want to know what your y value is doing as your x gets close to something. The guy you're interested in, put him in the middle of the table. You want to know when x is 0, what is going on with the y value. That's what you care about. But what you do is you just plug in a bunch of values getting close to that. And I mean super close to that. I don't mean like plug in 1,000,000 or something like that. Plug in something super close, like 0.1, 0.01, 0.001, 0.0001, etc. Right? From here, you're going to like minus 0.0001, minus 0.001, minus 0.01, etc. You'll notice that here you're going to get 10, you're going to get 100, you're going to get 1,000, you're going to get 10,000. You realize that, hey, as I come from the right a little bit above, I'm approaching infinity. The answers just keep getting bigger. Then you're getting negative 1 over 100. Sorry, it's already 1 over 100. You're getting negative 100, negative 1,000, negative 10,000. And you're like, well, as I'm coming from this side, I'm getting negative numbers, right? And then you're like, well, these guys don't agree. So that means your answer here would be, again, you would get the correct answer that this limit does not exist, right? But obviously, if your function here is complicated, then to actually do these calculations, it's going to take time and effort. And usually in person classes, I don't even allow students to have calculators in this class. You have to do everything by hand. And so you don't want to waste time with a table of values if you don't have to. It's very good for you to know a bunch of standard graphs and just have a good idea of graphing in general, which you learned in pre-calc. Because between graphs and table of values, if the graph is remotely possible, it's going to be the better way. You should know how to graph this in a few seconds, whereas filling out this table is going to take you a few minutes, right? So graphs or table of values would be step 4, if none of the above work. And again, I want you to go in this order. So don't try step 4 before you tried step 1, 2, and 3, right? You go in this order. Step 5. So here, I mean, this is sort of a special technique, actually. Use knowledge of the behavior of functions. which Jhevon told you about. This is in fact one of the special techniques. This is one of the special techniques, right? So this would be applied at step 3, actually. Useful is a relationship that I told you guys about before, is that logs grow slower than polynomials, grow slower than exponentials, grow slower than, I didn't tell you about these guys, and we're not really going to talk about them. But this is the last strategy, so we're going to be done after I explain this one. I know we're already over time. Yeah, so remember, and this is a relationship you can know as x goes off to infinity and our a is larger than 1. Okay, so basically remember what this meant. Guys on the right are huge compared to guys on the left, so that guys on the left are effectively 0 whenever this happens. So if I were to ask you, what is the limit as x approaches infinity of x to the 7th over e to the x plus 1? Well, you'll notice that the top is a polynomial and the bottom is an exponential. No calculations necessary. I know that the answer is 0. Why? Because x to the 7th compared to e to the x when I'm going off to infinity is effectively 0, right? This guy effectively is moving towards 0 over infinity, which is 0, right? That's right. On the flip side, if I gave you limit as x approaches infinity of e to the x plus 1 all over x to the 7th, then you're like, that answer is infinity, right? Because this is effectively approaching infinity over 0 with a slight positive charge, right? That is infinite, right? You have a big number and you're dividing it by a small positive number. You're going to get a huge positive number, right? So no calculations, no graphs, no table of values, no nothing. I can know what the answer is. And I can say, to show my work for this, you can literally just make the statement bottom heavy, and I'll know that you know what you're talking about. This one, you can make the statement top heavy, right? The bottom is much heavier than the top. It goes to 0, it goes small. If the top is much heavier than the bottom, it goes to infinity or minus infinity, depending on the signs, right? But that's just it. This is a special technique. If I have different kinds of functions competing with each other, then I can know by the class of functions how they're going to behave if we're going off to infinity. So this is very useful for limits at infinity, right? And those are the steps. Those are the strategies for now. I'm actually going to give you a couple more special techniques and strategies later, but in light of the above, try these examples for next time. I'll leave them in the notes. So if you have to go, you don't have to copy them now. Try these for next time. So I want you to use everything that we've learned, apply the strategies, and get to these answers. And we will pick up with these on Monday. It's funny how I tried to have one of those optional classes. We would have done these today, but everyone's like, hell nah. In that
I have
poll.
a quick question.
Yeah.
It's kind of irrelevant to what we've done today, but it's in regard to like the quizzes.
Mm-hmm.
Do you think it'd be possible, like I'm fine with Sundays, but would it be possible to do them like Sunday afternoons or like evenings because of like religious reasons? Sunday mornings are kind of difficult for me.
Sure. If you just email me and I'll set something up.
Okay, awesome. Thank you.
But yeah, definitely for like religious reasons, I'll make accommodations for sure.
Okay, thank you.
Yeah, just email me personally. So.
Okay. We'll
Yeah, so with that, sorry for going over time. Thank you for your attention, but we're going to end right there unless there are any more questions. I'll post a video later today with the notes and you'll have these problems and you should try them. And I encourage you to reach out to your group members and try them together as well. Okay, that being said, have a good rest of your day, have a good weekend, and I will see you guys in the next one.